I'm Sam. I'm the co-founder and CTO of Mysten Labs. We work on the Sui blockchain. We work on Move. I was also involved in the creation of Move when I worked at Libra and DM starting in 2018. So there's three things I'm going to talk about today. I'll start off with some motivation about, anytime someone's talking about a new smart contract language, there needs to be a strong justification for why bother with this and what's good about it and what's different about it. I'll then go into a little bit of a deeper primer on Sui Move, starting with some core Move features and then expanding a bit to some things that are specific to Sui. And then I'll do a little bit of a tour of some of the Sui-specific tooling we've built out for Move, the IDE support we have, the Sui Object and Transaction Explorer, and the Sui CLI, and maybe do a little bit of a live coding to show some of the cool stuff that we can do there. So let's start off with the motivation part. So I have sort of a strong take on the motivation here, which is basically that I think smart contract safety, based on the languages and developer ecosystems today, is an existential threat to broader crypto adoption. And the reason I say this is, you look at one of my favorite websites, rec.news, and you have this great leaderboard of big hacks and how much they're worth. And not all of these are smart contract hacks, but a large portion of them are. And this is sort of like the state of the world right now. Like $100 million plus hacks are routine, $10 million plus hacks are even more common, sort of like a weekly basis. And some folks will say, oh, it's because developers are cowboys and they're not careful enough and that'll be fixed. But in my experience, from the smart contract developers I talk to and have worked with, these folks are incredibly careful, they're incredibly conscientious, they're experts in the underlying blockchain, and they're really, really security conscious. I think they're like the best group you're going to get for trying to solve this really hard problem of writing safe smart contracts. And so if you want to grow the pie and add more developers to the community, these folks are going to be more product focused, probably less security and less security focused, have less expertise in the underlying blockchains, and the security situation is going to get even worse. So if that prediction is correct, either the smart contract developer community will sort of stay about the same size that it is today, and the security situation will stay about the same, or it'll grow and the security situation gets worse. And I think neither of those is a particularly good option. And so if we really want to grow this thing, if we want broader adoption for crypto, we need a bigger developer community. And I strongly believe that the only path to getting to that is safer smart contract languages and more advanced testing, analysis, static analysis, and verification tools that can open smart contract development to a broader audience while making things safer all the time. I think if we don't do that, we're just going to end up in a worse version of today. And so, of course, I'm going to be pitching Move as the candidate for this language. So let me talk a little bit about the problem of smart contract languages broadly. So smart contracts are these really kind of unconventional programs compared to the programs that we're used to writing or that I learned about in school. They're very narrow in their focus and their functionality. I claim that they really only do three things. So they define new asset types. You have a recipe for some type in the fields that it has. They define policies for reading assets, writing assets, and transferring them between addresses or between other objects. And then they enforce some access control conditions. Only the owner of this thing should be able to spend it. You can only touch this after this time, and these sorts of things. And so this is a very narrow domain. These aren't things you need to do if you're writing a compiler or building a mobile app, and there are lots of things you need to do in those settings that you wouldn't need to do here. And so if you have a language that's really focused around smart contract development, there's a lot of conventional language features that you don't need, and you need some that really aren't present there. In particular, you need safe abstractions for custom assets, for ownership, for access control. And you really need good language support for strong isolation. If I write a bunch of code and I have some invariants that I want to enforce, I'm going to open source it and publish it on the blockchain where motivated attackers can interact directly with it and try to steal money. I really want the language to have my back to make sure that my invariants are going to hold no matter what an attacker tries to do. So these are not common tasks in conventional languages where you keep attackers out of firewalls or just don't allow third-party code in your system at all. That's sort of the best practices for secure systems. And I claim they're also not well supported by existing smart contract languages. So to drive this point home, if you're writing a smart contract on the EVM or if you're a Solana smart contract programmer, you can't do the following things, which seem like natural things you'd want to do. Maybe I want to pass an asset as an argument to a function or return one from a function. I'd like to take an asset and store it in a data structure. I'm going to call some function, and I want to let them temporarily borrow the asset, but I want them to give it back to me once they're done. I want to declare some asset type in contract 1, and then in contract 2, I'm going to build a derivative asset type that uses that type in a field or sort of builds on top of it. Or even, I want to take the asset outside of the contract that created it. The conventional data model for assets is you have a hash table where the keys are addresses, and then the values in the hash table are bytes, and sort of the assets always live there, and the only way to interact with them is via whatever API the contract exposes for touching that hash table. Whereas what you'd really like is, you'd like to be able to take that asset out of the hash table and let it flow into another function or another contract, and use type-based abstraction like we do in ordinary programming. So what I claim here is that assets and ownership are the fundamental building blocks of smart contracts, but in existing languages, there's no vocabulary for describing them. And so this leads you to a really weird place where there's this thing that you're trying to say, but you don't have the right words to say it. And so if you're trying to talk about something like, have an asset that contains another asset that's expressed via a bunch of indirection pointers into hash tables declared elsewhere, instead of just declare type 1 and then type 2 is a field inside of it. And so in Move, what we're trying to do is we're trying to give programmers that vocabulary. We're trying to make assets a first-class citizen, express them with types, and then just make sure that this is really natural and really safe. So here's just like a little bit of sample code of like an example of how we show this. We encode both assets and ownership in the type system with these Rust-like linear types. So if you see some Move code that says buy, and it takes a coin as input and returns a card title, you should read this as saying, hey, this function is giving you an offer. It's saying, if you give me a coin, then I'll give you back a card title. And then we bring reference semantics into the mix as well. So in this next function, you say, I have this register, and it takes a reference to a card title, and then it takes ownership of a coin and returns a card registration. So this function is saying slightly different. It's saying, if you show me your title, it doesn't need to take ownership of the title. It doesn't need to write it. It just wants to see that you have it. And you pay me a fee. I'm going to keep that fee. Then I'm going to give you back a card registration. And of course, you don't want the language to have built-in cars and card titles and registrations. This is just a silly example. You want these to be user-defined types that can be declared in different modules and have custom data inside of them. And we want all these types to not be usable only in the module that declares them, but we want them to flow across trust boundaries without losing integrity, to be mixed and matched arbitrarily by other code in unexpected ways while still retaining their core safety. And so the way we make this safe is that we have a type system that's enforced by a bytecode verifier that runs whenever you publish move bytecode to the blockchain that prevents misuse of asset values in sort of the standard ways you'd expect. So you get protections against duplication. If you write some function that takes a coin as input, and then you write some code that tries to copy that coin, the type system is going to slap you on the wrist. That's an error that you're not allowed to do. Similarly, if you try to duplicate by taking a reference to something and then trying to dereference it, you also get an error. Another kind of common error that would be easy to do if you're using an ordinary programming language is like so-called double spending. If I have a coin and I'm trying to pass it to some function that's accepting the coin as payment, well, I better not be able to pass it twice. I better not even be able to use it inside of the function once I've moved it into pay. And so this is where the name of the language comes from. It has these different modes of using values. Sometimes you copy them, sometimes you move them, and once you move them, you're not allowed to use them anymore in the context where they've been moved from. And so also protection from destruction. You get some code that takes a coin as an input. I shouldn't be able to reassign the variable that's holding that coin because that would just drop the old coin on the floor. I'm accidentally throwing away money. That's something that I'd really not like to have. And similarly, if I don't use the coin, I just try to return from the function and leave C sitting there, you also want to get an error. You want to be forced to move C, put it in an address, pass it to another function, just make sure you get rid of it so it doesn't accidentally get lost. So these protections in aggregate are ensuring that digital assets behave like physical ones, which is a natural thing to want, but is a really hard guarantee to provide in a conventional language where everything's just bytes and it can be copied around, and you don't have any of these scarcity guarantees. And so with Move, we're setting up the language so that you get these by construction, and you can use it to define arbitrary rich types that are doing all sorts of different things. So getting back to the point about smart contract security, like you want nice abstractions for assets, but you also want things to be safe. Otherwise, like you're just not going to get to this better place. And so Move does a variety of things to optimize for safety and predictability, learning both from the lessons of Solidity and the EVM and from the other programming languages. So the biggest one is that there's no dynamic dispatch, which also implies that there's no reentrancy. This is a common source of vulnerabilities in the EVM world, and it's also just in general, like we think, not an appropriate language feature in a safety critical setting. Like if you have dynamic dispatch, you're allowing an attacker to define arbitrary code that gets injected in the middle of your code. That just makes it a lot harder to reason about what your code is going to do. In Move, every time you call a function, you know exactly what code is going to be called at the time you write the code, and you don't have to worry about someone else coming along and doing something unexpected later on. In addition, there's no mixing of aliasing and mutability. This is like Rust. We have a so-called borrow checker where if you're using references, it makes sure that you can if you have a mutable reference, it owns the data that it points to, and you can't mutate it and sort of lose the value behind your back. And if you have immutable references, then you can't mutate the data under those. So that's quite useful for ensuring memory safety. All of these properties, like the type safety, the memory safety, and so-called resource safety, like not doing the copying and dropping and this sort of thing, they're enforced by a bytecode verifier, so you can't get around them by just skipping the compiler and writing the code directly in bytecode. When you try to publish them, it'll be enforced directly, and it'll reject your code if it can't pass the verifier. And finally, for strong isolation, we set up the modules in such a way that they really encapsulate all of the types that they declare. And we have this recent paper that's showing that we get this security property called robust safety by default if you follow a set of simple rules. And then finally, like this is a smaller thing, but I think important, mathematically ill-defined operations like integer overflow, division by zero. These are sources of bugs in many other languages. In Move, all of these abort. If something is not well-defined mathematically, it just crashes. Basically, you get safe math by default if you're familiar with that library in Ethereum. And finally, we've co-developed the language from the beginning with a formal verification tool called the Move Prover. All the things I'm describing above are built-in safety guarantees that the language itself gives you. But then the Move Prover allows you to write user-defined safety properties that are specific to your application. Something like, only this user should be able to access this particular object, or the number of coins that I've minted matches the total supply in this object. Things that are fundamentally application-specific, and the prover can look at them and make sure that no matter what sequence of transactions are called, no matter what other smart contracts interact with this property will continue to hold. This is the highest correctness guarantee that you can get. Testing is great, and you should test as well. But if you have formal verification, then you really get the maximum safety. And finally, and I think like this part is maybe the thing that's the most different about Move compared to a lot of these other smart contract languages. It's designed to be platform agnostic. So the status quo elsewhere is that if you're creating a new blockchain, it's probably either and sort of an Ethereum clone, or it's defining a totally new language. And so this happens because most of these languages, including the EVM, they tend to hard code a lot of the design decisions of the underlying platform into the language itself. So the account format, the transaction format, serialization format, the cryptography that's used, maybe even the consensus that's used, things like the block structure. And so what that means is, if you're trying to define a new blockchain platform, maybe you're trying to address some scalability problems with an old one or some usability issues, and you want to use an older smart contract language with an existing community, you basically don't have any freedom to make new decisions in those areas. Whatever decisions the language commits to, you inherit them and the limitations that come along with them. So with Move, we've done things intentionally to be agnostic for all the things above. The core Move language is very, very minimal, and it doesn't have things like accounts or transactions or coins. And so what that does is it allows platform to design. It's designed to be this embedded language where you use Move in your blockchain, and you write this little component called an adapter that takes your transaction format. It knows how to turn it into a call to a function to the generic Move VM. The Move VM outputs some effects, and then your adapter decides, how do I apply the effects to my database or my data format? And so what that does is, it just makes it a lot easier to use Move in blockchains that look really different under the hood. Platform designers can experiment with different choices for all of these things. Programmers who are using Move on one chain can hop over to another chain, and they're using the same compiler, the same virtual machine, the same verifier, all of the tooling. Many of the libraries will just work seamlessly across platforms. So you don't have, as a developer, you don't have to bet on just, okay, I think this is going to be the blockchain of the future, so I'll like spend a lot of time learning this, and then bet wrong, and you go somewhere else, and your skills are no longer useful. If you learn Move, you can program on multiple blockchains today and on many different ones in the future. So it's very early in seeing this theory come to fruition, but even today there's 5 Move-based blockchains that all look quite different under the hood in how they work. So there's Sui, which I and Mysten Labs work on. There's Aptos, there's OL, and there's Starcoin. And there's lots of interest from both existing and emerging chains to add Move as a second language for that chain or to launch a new Move-powered chain. So we feel good about the design that we've actually made this in a platform-agnostic way. And really the vision we have for Move is that we want this to be the WASM of Web3. This is sort of the execution layer, the VM that runs when you have smart contracts that interact with assets that are doing anything security critical. And you can, as a developer, you can learn Move and you can use your skills on whatever new platforms are coming out. So that's the end of the motivation bit. I'm now going to go a little bit deeper into some slightly drier material on Sui Move, just to learn the basics of Move so that we can go into some interesting examples. Maybe a good time to pause for questions in the meantime. All right, well, just keep on rolling then. Okay, so let's look at some of the sort of building blocks of Move code and how they work together to build programs. So in Move, the minimal unit of abstraction, sort of the equivalent of a class or a contract or whatever you're familiar with elsewhere, is called a module. So when you declare something like a module, it has a parent package name. So here, the package name is DeFi, and then the module itself has a name, and the name is /lender. And when you declare a module, you can reuse code and types that were declared in different modules. So here, this /lender is reusing a type called coin from the coin package. And so this is how we allow this trust boundary crossing code reuse thing. When you write this code, it's not copy-pasting source code from somewhere else. It means somewhere else in the blockchain, there's a module published called coin, and I'm actually linking against that bytecode, that type there. And similar for functions, you don't publish multiple copies of the same code. And then there's this notion of a package. A package is just a bundle of modules that are all published together. It can have features like friend, visibility that you can't use in a different package, just a convenient way to put together a bunch of related modules. So let's talk about Move data types for a minute. There's primitive types like Booleans. You have unsigned integers, U8, U64, U128. You have addresses, which are the way you identify the owner of an asset or the sender of a transaction. And you can have strings. There are two different string types. There's the standard string, which is UTF-8 encoded, and then there's also ASCII encoded strings. There's built-in collection types, like a vector. You can push values into it. You can pop values off of it. You can get references into it, very much like the Rust-vec, if you're familiar with that. And then the bread and butter of Move is these struct values, which are user-defined and can have fields of any type. So you might say, struct mystruct. You have an integer field whose type is U64. You can define another struct as a Boolean field, and then of course you can nest structs arbitrarily, so this mystruct has another struct inside of it. Okay, so let's look at abilities, which are how we get to these protections about copying and duplication and the things I talked about before. So these things are implemented via what we call abilities, which decorate types. And each ability, the way you should think of it is that it gives the type permission to do certain things. And if the type doesn't have that ability, then it doesn't have that permission. And so mixing and matching these in different ways lead to very interesting results. So this first one is a typo. That should say struct C has copy. If a struct C has the copy ability, that means that C can be duplicated. Basically, you can do a mem copy of it. So something like an integer, of course, would have the copy ability, but if you were defining a coin, then it should not have copy. And so if you don't have copy, the only way to create a struct of that type is inside the module that declares the struct. So you have this nice privilege creation behavior. Then drop is sort of the mirror image of copy. If you give a struct the drop ability, that means you can indiscriminately get rid of it. You can return from a function without using it. You can overwrite it by reassigning a variable, and all of these sorts of things. Again, like a string would have drop, an integer would have drop, but something that's valuable like a coin or an NFT, you probably wouldn't want to give it drop unless you just want to let somebody get rid of it or destroy it by accident. And so if a struct does not have drop, then the only way to get rid of it is via an unpack call inside the module that declares D. So this means in Move, you can define values that can't be destroyed or values that have conditional destruction. You can only destroy this value if you pay $10. That's a policy that you can write if you want to. So then let's talk about key. So Sui Move has this global storage that's organized as a map of objects from object IDs to objects. And if you want a struct type to be allowed to appear in the global storage, you have to give it the key ability. If you don't have it, there's a special function that I'll show you in a moment for putting an object into the global storage that you won't be able to call. Then you have store, which is also related to global storage. So what store says is, I'm allowed to appear as a field inside of a struct that has the key ability or the store ability. And so if you could give something store but not key, and what that means is, well, I can't be a top-level object in the global storage, but maybe I could appear inside of it. And so this is useful both for custom struct types, say like coins, but also something like string or U64 that would have store too. You want to be able to have global objects that have those inside of it. And then finally, you have this so-called hot potato. What happens if you give something no abilities? So what that means is that it doesn't have drop, and it doesn't have store, and it doesn't have key, so there's no mechanism in the language for getting rid of it. The only thing you can do is pass it back to the module that declared it to unpack it. So as we'll see later, this is very interesting for things like flash loans, or sort of like you give somebody a hot potato and you define a policy that forces them to eliminate it in a certain way, which is a kind of a cool feature of Move that helps us work around the absence of dynamic dispatch. So let's talk about Sui objects specifically. So I mentioned this key ability. So there's one other rule with key, which is that if you declare a type that has the key ability, you also have to give it this ID field, and the ID field has to be of type Sui object UID. Now, what's this UID thing? This is a globally unique identifier for an object. There's an API in the Sui standard library that allows you to derive a new globally unique object ID from the hash of the current transaction. And so every time you want to create a new object, you do object new, you get an ID, and then you put it in this field. And so this thing is important because this is the way an object is identified. When you have a transaction that's using objects, you say, hey, here are the IDs, the objects I'm going to use, and then the Sui runtime knows how to take those IDs and resolve them to objects by looking at the Sui global storage. Okay, so then there's these different object ownership modes. Let's say I have an object that comes in as input, and I'd like to give it to a user. I'm Bob, and I'd like to give it to Alice. So there's this Sui standard library function called transfer, and so you can transfer any kind of object type to any address. So if I get T as an input, and I get adder as an input, and I call transfer T adder, now T is gone. It's been moved into transfer. And T can only be used, in the future, T can only be used in a transaction that's sent by adder. If somebody else tries to touch it, they won't be able to. So this is nice for things like coins or NFTs that are owned by a single person, but if you want something that many people should be able to touch, maybe it's an auction, maybe it's a DEX, or these sorts of things, maybe it's a balance that you'd like to let somebody borrow from while you also spend from it, then we use what's called a shared object. So the way we use that here, here's a function. It takes some T as input, and then it just says Sui transfer share. And so what that does is it writes T into the Sui global object store, and it assigns its ownership metadata field to shared. And now anybody can send a transaction that's using this T object, but of course they can only use it according to whatever policy the module declaring T ends up implementing. Like in a DEX, maybe it would say, you can use this object, but use means you can swap a currency of one type for a currency of another type if you pay the fee, and these sorts of things. So let's talk about function visibility. There are basically 5 different modes, and these can be mix and match. So the first two of these are the first ones of these are sort of the funkier ones. There's this notion of an entry function. An entry function means that it can be called from another transaction. When you have a transaction in Sui, it has a sender, it has a public key, it has a signature on it, and then the way it encodes the Move smart contract it's going to call and what it's going to do is it specifies, here's the on-chain package object that I'd like to call, here's the name of the module, and then here's the name of the function that I'd like to call. And then the rule is that function has to be declared as an entry function. So if something is just a normal private function or a public function, then you can't call it from a transaction. And so if you say public entry, what that means is I can be called both from another module and from the transaction at a top level. But you can also omit the public part. You say this is an entry function. And so what that means is I can be called from a transaction or inside the current module, but not from other modules. So that's sort of an interesting option. If you're trying to intentionally write a module that can't be composed with other modules, like let's say I'm trying to write a DEX, and I want to make sure that nobody runs flash loans against my DEX. If you expose your DEX functions as private entry functions, then what you know is they get called from the top level, but sort of not from somewhere else. So that can be an interesting way to prevent interactions with other modules, if that's something you'd like to do. Whereas if you're trying to intentionally make your code composable, which I think would be the common case, you would use public entry. So of course, you can also declare a private function. This is like everywhere. You can only call it in the current module, but not from outside. And then, of course, you can declare a function public, which means it can be called by other modules, but not from a top-level transaction. And finally, there's this notion of friend. We talked earlier about packages, where packages are these bundles of related modules. One module can declare other modules in the same package that are friends, and then this means that my friends can call it, but other functions outside this package can't call it, and non-friend modules in this package also cannot call it. Okay, and then the last Sui-specific thing is module initializers. So something you often want to do in Move is you want to create an object that's a singleton. There's only one instance of an object of this type. So an auction looks like this, a DEX looks like this, maybe something like an escrow looks like this too. You don't want to allow somebody to create an unbounded number of modules of this type. You just want there to be one such thing. NFT collection, that's another example. So there's a convention that if you name a function init and you give it this special signature where it takes this TX context thing, which I'll explain in a minute, then this thing will be called when you initially publish the package, and it gets called exactly once. So that's very useful for initializing singleton objects. You create a bunch of objects in here, you know init's not going to be called again, and you just don't create other objects of that type elsewhere. And so that ends up being quite a useful thing that doesn't exist in core Move. Okay, let's actually write a little bit of code. We've been doing some dry Sui and Sui Move primer a bit, but any questions on the previous primer parts before we dive into the code examples? All right, everyone else is tired on Friday afternoon as well. All right, so let's look at the flash loan bit. So what we're trying to do here is we're trying to define a generic flash loan. And of course, this might seem hard to do at first because we're in Move, we don't have dynamic dispatcher interfaces. The way this works in something like Ethereum is that you have a flash loan interface, and it basically takes a callback as input, and it makes a loan first, and then invokes your callback, and then calls something else that forces you to pay it back. But that implementation option isn't available to us, so we have to do something different, which is kind of interesting. So here we're going to define the struct. We'll call it a flash lender. There's this thing that says phantom T, and what that thing is it's the type of the coin that we're going to allow loans against. And what phantom means here is that I don't actually have an instance of T inside a field of the module. I'm just going to bind it to other phantom usages. This thing has the key ability, so we have to give it an object ID. And then I have this field toLend that contains a big pool of the coins that I'm going to lend out in my flash loans. And then finally, but just to keep it simple, there's going to be a fee for folks that are taking out a loan, and we'll just make it a flat fee. Maybe we'll charge 10 Sui. In practice, it would probably be a percentage of the loan size. And then there's this other type we're going to define that's called receipt. And so what this thing does is it remembers the ID of the object, of the flash lender object that it borrowed from. And so here, note that this thing is Sui object ID rather than UID. UID is globally unique. You only create it through this special object new function, and it's guaranteed that there's no two IDs that are the same. Whereas object ID is more like, I can type in 72 and then turn that into an object ID. It's a pointer to an ID rather than this privileged, guaranteed to be unique thing. And then with receipt, it remembers, okay, here's the lender I borrowed from, and then it also remembers, here's the amount that I need to repay. And note here that receipt doesn't have any of these type abilities. It doesn't say has anything, and so what that means is it's one of these hot potatoes we described earlier. It can't be stored in some other object or dropped on the floor or transferred. We're just going to have to get rid of it, however this flash loan module is telling us to. So let's look at the loan and repay objects here. So loan is going to take a mutable reference to a flash lender. This is the flash lender object that we're taking out a loan from. It takes an amount of coins that we're going to borrow. and then it returns the coins that correspond to the loan, so that'll be a coin that's worth amount, and then you get back this receipt thing. And the thing to notice here is that you can't take out a loan without getting back the receipt. And then you have the repay function. This is going to take a flash lender as input. It'll take back the payment that should correspond to the amount of the receipt, and then the receipt that tells you how much you need to repay. And so the key idea that makes this thing work is that you get back this receipt thing. There's no way to throw it on the floor or toss it away or just get rid of it. The only way to get rid of it is to call this repay function. So you call loan, you go and take your coins, you do whatever you're going to do. You do an arbitrage, whatever folks are doing with this flash loan. And then once you've done that, you'll be forced at some point to call repay, or your code won't even type check. And so you can try this here, like someone is trying to use the flash lender, they call loan and they do loan receipt and then they do nothing else. And if you try to do this, like here, I'm just trying to take the loan and steal it and transfer it to myself and ignore the receipt, the compiler is going to yell at you, or if you wrote this in bytecode, the verifier would yell at you. It'll say, hey, receipt still contains a value, you're going to need to get rid of that, or I'm not going to produce code for you or verify your code. And so this is sort of the flash loan in a nutshell. I didn't show you the bodies of the function, but these things are quite intuitive where, in loan, we grab some coins out of that bigger pool, and then we create a receipt whose value is the value of the loan that I got in plus whatever the fee is. And then inside of repay, we take in the receipt. We make sure that the coin that we're given is corresponding to the value of the receipt, and then we put that coin inside of this two-len pool. So let's talk a little bit about the available dev tools. So there's the VS Code plugin that we've been working on. It's called the Move Analyzer. This is an open source VS plugin. This is an open source VS Code plugin that utilizes the language server protocol. So it would be easy to take this and adapt it to a different editor like Eclipse or Sublime. It supports all the sort of basic things you want from your editing experience. You get syntax highlighting, you have compiler diagnostics, you have go-to definition of references, you have go-to type definition as well, and when you hover over types, you can see those as well. So the things in the VS Code marketplace, it's linked to from our dev docs, and you can grab it. Here's a picture of the page on the Visual Studio site. And then we have the Sui Explorer, which is quite dev-focused. If you go to the main page, you can see all the recent transactions. You can see what kind of transaction type is happening. So call is the most interesting and sort of common one. That means I call to move smart contract, and you can see the ID of the transaction. It'll tell you the sender of the transaction. And then if it's a non-call transaction, there are special transaction types for transferring Sui that bypass the move VM, and so you can see like how much is being transferred and how much gas is used. And then also you see how many you can see the current validators and the full nodes and where they are. Here is our DevNet, so there's just 4 validators, what countries they're in, all sorts of things like that. And the team is working on adding many more tabs with various features in here. So when you go into here, you can click on a transaction, and you sort of see the Sui object model in action here, where you can see what objects the transaction updated. You can see, these are object IDs here. You can see what objects the transaction created. In this case, you can see how much Sui is transferred. You can see the sender and recipients. If it emitted events, you'd be able to see it in this bar. You can click on the signatures to see the signatures of the validators, if that's interesting. There's also an address view where you can look at an address and see what are all the coins it has, what are all the NFTs it has, what other objects, what transactions has it sent since the beginning of time. A nice way to see all the action associated with some address. You can also do a deeper inspection of an object. So here we've got this object. We can see its ID. We can see its move type. And so the structure of the type is there's this long thing here. That's the object ID of the package that declares the type. This Sui name NFT is the name of the module. And then this uppercase Sui name NFT is the name of the type. And we can see the last transaction that touched this particular object. We have version, which gets incremented every time you use the object in a transaction. And we can see the address that owns the object. And you can see there's properties. These are the fields of the object. So there's a field named URL, and it points to this URL. And the Explorer has this special interpretation for some pairs of name and type. So if you create a field called URL and its type is URL, the Explorer will know I shouldn't just show the URL string. I should also go and look for an image of that URL and display it here. So this is what that's doing. And so this will work for any type. There's nothing special about this Sui name NFT. That's actually a community type where someone is just leveraging this nice object visualization feature of the Explorer. And finally, and this is one of my favorites, you can inspect published code. So if you click on one of the package objects, you can see the object ID, the version, the address that published the package, and then you see the decompiled bytecode. So here, no one has published the source code for this particular package, but you can see that the decompiler still gives you quite a bit of information. You can see, basically just like in source code, the names of the structs, their types, and then it doesn't show it here, but there's also go to definition. So if I clicked on vecmap, it would show me the declaration of vecmap, very much like having an IDE based on bytecode. And of course, we're working on allowing you to upload verified source code as well, so you can get even more detail than this. But for any code, you get at least this much info, which is quite readable compared to something without types or decompilation. So there's also the Sui CLI. These instructions are in our docs, but you can install it for the latest DevNet branch, and so you can do all the things you need to do with interacting with the Sui network and with Move. You can build your Move code, you can test it, you can run the Move prover, you can publish your code, you can run Move calls, you can inspect objects, basically all the things you can do in the Explorer, and then a little bit more. So this is really nice for sort of playing around with your app, but then if you're trying to build an actual app, we also have Rest SDKs and TypeScript SDKs and are working on C# and a couple of other languages. So you can interact with the Sui blockchain, craft transactions, sign them, and all of those sorts of things directly from the app. So let's see. Yeah, let's do a little demo. We have time for this. So we'll just write a very tiny project here, I guess. So here I have the Sui CLI. So if I do Sui, I can see all of the available commands. So if I want to create a new project, I just do Sui move new, and let's call it, Converge example. And so what that gives me is a new directory called Converge example. So I go in here. I've got a move.toml. This is a manifest file that has the name of the project. It automatically creates a dependency for me on the Sui framework at the version of the DevNet, so I can use all the Sui standard library and those functions. It adds some addresses for me, and then it creates a sources directory. And then so if I wanted to start writing some code here, what I would do is, let's see. Let's call it example.move. And here we'll call it, what do I call this thing? Converge example. This should be the name of the package. And then I'll call my module example. And then I'll create a struct called s. I'll give it the key ability so we'll be able to publish it. And you can see, I'm in the IDE, so the plugin is running and it's suggesting auto completions and all these sorts of things. And so let's use Sui object so I can get the UID. And then we'll give this a U64 value. And then let's just define a module initializer that publishes it. So fun init. We need to give this a TX context. And then we're just going to make a shared object out of this thing. So here I'm calling share. This is constructing an object of type S. I'll need to create an object ID, which I do with object new. And then I'll bind v to, 7. That sounds good. Okay, so this is basically the minimum possible move package I can define that actually does something. So I'm pretty sure I made a mistake in forgetting an import here. So let's just look at how the compiler will tell me about that. So I would say Sui move build. This is going to take a second because it needs to download this package from Git and then put it in the cache, but it'll be fast after we call it the second time. In the meantime, I'll try to anticipate the mistake that I've made, which I think is forgetting TX context. still waiting on that. Let's add one more field here. This is always the problem with live demos, huh? Okay, let's do something more interesting, like adding another struct to kill some time. So let's say we actually want to put another struct inside of S, so it's just not too simple. We'll say struct t has store. We need to have store because we're going to put it inside of S. We'll give it another U64 field. And then we'll need to put that here. And then you just sort of do what you expect here and put the boy, okay, that download is really taking some time. All right, I'll hop over to the Explorer and then come back here. So here's more of the live view of the Explorer, so you can see, the folks are doing things. If we look at a recent call that someone's made, so here they've called this DevNet NFT. They've called a function in the Sui standard library that has this special address 0x2. The module name is DevNet NFT. The function name is mint. You can see the arguments that they've passed to this function. So they pass some string called ethos 2048 game, and then they have a nice message that someone's an expert, and then there's this nice Arweave URL. And then if we click on then we see, as I was showing before, we can see what this transaction did is it updated the coin that we used to pay for gas in the transaction, and then it also created this new object. So here it created something of type DevNet NFT. You see that it's got that's the URL which it would have fetched from this Arweave location, and then it's got this description which shows up as a string. And then if we want to go back and we want to look at the code for this package, then here's the move standard library, and we can see all of the code that's in here. This has a bunch of different modules. It knows that it was published at Genesis. Okay, I see that we're back here. Okay, so we got an unexpected token. What have I done? Okay, I forgot a comma here. Okay, so we move build. That was a lot faster because it's done the download. Okay, you're right. And the other thing I forgot is to import the object and transfer. So we'll do that. And then because I want to use a function from object, but not a type from object, I write self here. And then so. Oh, right, it's called share object, not share. I should really know that. Yeah, the IDE knew it. Okay, so now the build works, and so now I can actually just go right ahead and publish this code. So I write Sui client publish, and then I have to give it a gas budget. I'm going to give it 5,000. And that's going to run. Okay, so now it tells me everything that happened. I created some objects. So I created this shared object. It says, okay, I created a shared object. What was that? That was this S object that we did here. I created an immutable object. That's the package object that contains the code that we wrote, and then mutated an object. Here, I'm running from a local account that has some gas coins I can use to play with the network, and so it's mutating the gas coin that I used. And so then, if we want to actually go and look at either of these objects, like let's take this and take it into the Explorer. I just put it in the object view, and then I see here's an object ID that was derived from my package when I published it. Here's the module named example. Here's our type name S, and here's the object ID, and here's basically exactly here's the JSON rendering of the value that we created. And then if we go to the package ID, we can see the decompiled bytecode of what we wrote. Looks very similar to the source until you get into this part when you see some real bytecode in action. And then if we wanted to look at, I guess, yeah, that's about it, because we've looked at the gas and we've looked at the package. And then, of course, if we go to the main Explorer page, we'll see Is this my call? No, someone else did that in between. So people are using the Explorer so rapidly that my transaction got pushed down, but it's somewhere down there, and we would be able to see it appear. So that's it for the demo. Let me return to the slides to conclude, and then we have lots of times for questions, as it turns out. Okay, so move and Sui. Sui takes move, which is this generic language for programming with objects, and then it marries it with this nice asset-centric data model that we have in Sui. Move provides these safe and convenient abstractions for programming with assets. It's intended to be this multi-platform language. And then I didn't go very deep into Sui today because I was focusing on move, but there's a lot of ways that Sui leverages the combination of move and this unique data model to do various things that really we think are going to be useful for next generation blockchains. You get this more direct move programming style. You can have safer wallets because a Sui transaction, as we were seeing in the Explorer, tells you exactly what objects it's going to act on, so that makes it easier to give the user a sort of human readable permissions request, like, hey, is it okay if I use this object? Is it okay? And then how am I going to use it? Am I going to transfer it? Am I going to read it? Am I going to write it? A lot of Sui's scalability comes from the fact that we have these move objects directly represented in the transaction data model, so we can see when transactions are independent and schedule them for parallel execution, and in some cases do faster forms of consensus. It also makes it easier to discourage contention because we can see when a lot of transactions are touching the same object, and we can charge higher gas prices for those transactions. And then finally, if you want third-party ledger validation that doesn't have a cost proportional to the total number of transactions, you can sort of use the fact that Sui transactions know the objects they touch to say, hey, I want to do third-party ledger validation, but only relevant to these objects or these addresses, which is quite interesting and different from only having the option to validate the entire ledger. So here's a bunch of resources, both on Move and on Sui. There's the Move GitHub repo. There's this awesome Move content aggregator that we maintain under Mysten Labs. There's the Sui repo, which is open source. There's our doc site, which will also have links to our Discord and to lots of Move content in various builder groups. And then, of course, there's the Explorer, where you can see all the latest action happening on DevNet. That's all I have for today, but lots of time for questions, and also happy to talk to folks one-on-one about Move and Sui or anything else of interest after the session. Thanks a lot.